So the last thing in the differentiation chapter is rates of change, so section 9.10. Now, really there are two things going on here. We've got things like example 29 and 30, which I'd think of as a rate of change question, and then we've got things like 31 and 32, which are setting up differential equations questions. Now, setting up differential equations is a bit annoying because we're not going to learn much more about differential equations and we're not going to learn how to solve them until the integration chapter. But it's quite similar to these other examples, so the textbook writers have put it in here. Then in example 33, we kind of do a bit of a mix of the two, all right? So I'm going to treat these as separate questions. We're going to do things like example 29 and example 30 as one method, and then the second thing is setting up differential equations, which we'll see as a separate thing. Now, example 29 and 30, I'm hoping this is somewhere that I can help here because these are often fiddly questions, and I think I've got a helpful way of doing this, that's something that students have found helpful in the past at least. If we read the question, we'll find that we've got various letters involved, and what I'd suggest you do, even in the exam, get a pencil in the corner, just make a few notes, right? So given the area of a circle is A, so we've got an A involved, is related to its radius R, so we've got an R involved. We've got a formula that links A to R, so we've got A equals pi R squared, and the rate of change is given to the radius, so we've got a t involved, right? So the rate of change means the rate of change over time. Unless they specify something else, it means the rate of change over time. So as time moves on, we get dr by dt, okay? And what we're asked for is dA by dt. We want to find dA by dt, the rate of change of area with respect to time, when r equals 3. We'll not worry about when r equals 3. dA by dt is what we're trying to find. Now, with these questions, what have we got? We've got A, we've got R, we've got t. So it's about derivatives and different derivatives linked to each other. So what options have we got? Well, we've got dr by dt. We could do dA by dr. And when I say what options we've got, I just mean, well, how many ways are there of combining A, R, and t, right? dr by dt, dA by dr, dA by dt, dr by dt. These are all the possible ways of arranging these things, on the top and the bottom. dr by dA, dt by dA. Those are all the possible options, right? R and T, A and R, A and T, one on the top, one on the bottom. Now, if you know dr by dt, you also know, one should be dr by dt, one should be dt by dr. If you know dr by dt, you also know dt by dr, because 1 over that is that from a result that we've seen earlier, okay? So really, we're not bothered about which is on the top and which is on the bottom, we're bothered about the pairs. So we can have A and R, we can have A and T, we can have R and T, okay? The one that we're trying to find is A and T. We know A is linked to R, so we can find dA by dr. We know R is linked to T, and it tells us in the question dr by dt. So we've got those two, and we want to find this one. So how do we do that? Well, what can we sort of shove together of our derivatives? Well, if we do this, dA by dr, dr by dt, then by the chain rule, that times that is equal to that, isn't it? dA by dr, dr by dt. You can think of it as though these r's cancel out, okay? Well, dA by dr I can find because it's 2 pi r. Just differentiate this with respect to r. dr by dt I can find because it tells me in the question the rate of change of the radius, that is the rate of change of the radius over time, is given by 5. Okay, so dA by dt is 10 pi r squared, and from there it's easy to find out the value of this when r equals 3. So that is when r equals 3, that is 9 times 10, which is 90 pi. Okay, now that might seem a bit of a convoluted way to do it, but when you get into the trickier questions, trust me, this is a helpful way of thinking about it. So let's go into the next one. We've got a volume of a hemisphere, V, so we've got V. Reading on, we've got a radius involved. We've got V in terms of R. So V and R, we've got a link between V and R, so we can find dV by dr, and we can do 1 over that to find dr by dV. So if I need dV by dr or dr by dV, we're sorted. We've got the surface area S, which is given in terms of R. So we've got S and R linked. I can find ds by dr, and I can do 1 over that to find dr by ds. So I've got that one sorted. And then the rate of increase in volume. So I've got a T involved as well. So I've got a V, an R, an S, and a T, and I've got V and T linked, sorted, okay? Because I've got dV by dt equals 6 in the question. Find the rate of change of surface area, S and T. So what I want is ds by dt. So if I want ds by dt, I need to have ds by d something by dt. Okay? Well, d something by dt, well, my only option out of the things that I've got is dv by dt, isn't it? So that's going to have to be dv by dt there. So I'm going to have ds by dv, dv by dt. So I've used that one up. So maybe you can cross that out, possibly. Now, I don't have ds by dv. So what have I got? Well, if I want ds by dv, I'm going to have ds by d something by dv. And then I'll times that by dv by dt. So what can go in here? Well, if I had ds by, what I've got is ds by dr. So I could have ds by dr, dr by dv. And now we're sorted. ds by dr I can find, because I've got a formula that links s and r, so I can find ds by dr. So take that and differentiate with respect to r. dr by dv, well, I've got a formula that links v and r. So I can find dv by dr and do 1 divided by that to find dr by dv. So I've got that one, and dv by dt, it tells us in the question, is 6, so I've got that one. So I know that, and I know that. Now the tricky bit here is getting to this. ds by dt equals ds by dr, dr by dv, dv by dt, because why would you think to put those three together in a chain? My suggestion is we do it this way. We think we've got a v, an r, an s, and a t. Then we look at what pairs of those the question gives us. If necessary, we think of all the possible pairs, right? dv by dt, dv by... So v and t, v and r, v and s. T and r, t and s, r and s. So we think of all those possible pairs. And then once we've got all the possible pairs, we tick off the ones that we know, we circle the one that we're trying to find, and then sometimes you're sitting there thinking, well, I can't find ds by dt. What things could I possibly put together that kind of total up to, you know, this by this, and this by this, and this by this? Well, sometimes you kind of go, well, if I just knew ds by dt or dv by dr, then that would sort the problem out for me. And then when you reread the question, you realise there is a way of finding dv by dr, or dr by dv, or whatever it happens to be, all right? Starting this way, though, ds by dt is ds by d something by dt. What can you put in there? It's going to have to be one of these four options, t, v, r, and s. ds by dv is the next problem that we've got, and that can be, we can shove a dr in there and a dr in there, and it all kind of works. And this, by the way, again, we're using the chain rule here, and we're using the chain rule here. Can you see there's a sort of, the r's kind of link these two, the v's kind of link these two. So there's a sort of link here and another link here, and the chain rule sort of chains its way along. That's really the reason it's called the chain rule. Okay, so that is things like example 29 and 30. We're already a long enough video, I think, so we'll stop and do example 31 and 32 as a separate video.